as
yep.
part of an internship
Yep.
on browsing large sound archives with determinantal point processes.
Yep. Yep. Okay. Well, thank you for your time first. I pretty much came up with this idea of foraging during an internship motivated by the use of generative systems. So probably they are very much everywhere. And I was really concerned that it's kind of like this end-to-end process where there's not much interaction in between. And since I am a music collector and generally a collector of things and fragments, I thought that something that could help me to forage or find the interesting bits could be really useful as an application in generative audio. So this is how I came up with this idea of foraging, which is very much a proposal for finding interesting stuff in large collections. So today we going to go through a little bit of the history of what these collections are, what have been the sort of main techniques in the library sciences and bibliography to index fragments of different sorts, because I think these techniques are right now, well, in a different stage in the digital world where all media and all the assets that we have are indexed in a way that reflects or at least borrows from some of those principles in the indexical overflow part. Overflow because it's massive, like so much information out there that the current methods we have, I don't think they are enough, so everything's becoming kind of like spacey dry in this dark forest internet, if you like. So it's becoming increasingly difficult to find the things that are worth it or the things that we actually like to interact with. So after that, I come up with the solution. It's like, well, not really a solution, but it's an approach. How do we deal with this accumulation of data? And finally, I will present just some parts of what was the main product of the internship, because the rest is being filed for a patent, so I can only show like bits of it. But it's not really something like you couldn't come up with yourself, I think. So what is the question I'm interested in addressing with audio foraging? I think that this data, maybe we don't have words, or maybe we will never have enough words to describe. So the idea of an open or a non-logocentric archive pretty much means ways that we can access or retrieve information that don't rely on linguistic input and involve more of an interactive or multimodal engagement with those sources of information. So this means that there will be no kind of unifying, all-encompassing index, and also no universal taxonomy. So one of the first general indices or universal indices of content was proposed by Konrad Gessner. It took, I think, like 10 to 20 years to collect like 10,000 books, arrange them into categories and so on, and then come up with an index in order to address what was by then the first century of the printing press. So all the materials that were produced during the first century of the printing press were the field of Gessner. So the field that Gessner worked quite hard to index with his own system. And then we have as a potential precursor of information retrieval systems and also generative systems, cabinets like this, which were used by Leibniz to write, to recombine, to create your own collection of things. Like when you're reading, you might have maybe your own strategies to store your fragments. Maybe you put everything into a Word file and then you use the search function. Maybe you use something like the Sedderkatzen, which is like a German method to arrange fragments. But this is reflective, I think, of the way that some of the audio fingerprinting systems work. It was all paper back then, and all these cabinets and systems are metaphors that then were digitized into directories and so on. So all this is part of that cultural history of automation, which is why I am doing this work. My research is focused on this process or media archaeology of specifically machine listening, which is all about indexing sounds of different sorts, like a Shazam for everything, if you like sound event detection, or it's got different names. But you get the idea. Then after those two examples, and Melville Dewey came up with a system, a more formal system of arranging library contents using numbers. And this is closer to the way that hashing functions work, or contemporary systems arrange libraries. And after that, we have kind of like more like a modern version of the fingerprinting methods, which were advanced by companies like Shazam or SoundHound and similar. And all these we could say that they are a kind of cabinet of excerpts that is indexed according to mathematical function that will retrieve all these fragments based on similarity. So the idea is that you can optimize the time that it takes to create those matches. So just generally there, I'm showing how those systems work. You have a node database, which could be your own personal archive. This database is pre-processed, is turned into like a cabinet, and then you have an audio query that will create a key that then will retrieve the closest match according to the hashes. So this is automating what was done by hand in the cabinet case and in the case of Melville Dewey. And then finally you have the result, which is could be a search result, or could be a fragment in a generative system that then will be recombined with something else. And then on the right side over there, we have more modern methods, which is automates that hashing part. So it automates the feature extraction instead of using some predefined filters or wavelets, like in this case. Then you parameterize those filters with an artificial neural network. And then the way that it's done is that the training inputs are pairs that then you deem similar or not, and then the system approximates a metric in the space of all the fragments. So then you can recombine and do something like subsampling or oversampling, and then you obtain an embedding for your audio fragment that you can use to retrieve information, to classify, and so on. So the challenge now is that the sounds, libraries, we could have, excerpts and summaries. It's kind of verbal. We have, language to describe those contents. So we use language in order to describe language. But the challenge with sound is that it's not that simple to come up with a standard way of describing sounds or arbitrary sounds. Like, just think about how would you describe when you wake up the scene that you're listening to. That's non-standard. So in the case of sounds, which includes music, all possible sounds, we don't have something as neatly as organized as this. So the thing we have in place of those systems, one of the most ambitious ones is called AudioSet. And AudioSet is an ontology, very much a taxonomy, which was created using 10-second samples from YouTube. And then those 10-second samples were labeled by people using something like mechanical torque or a system. So the retrieval was algorithmic, but then part of the labeling was done by humans. So it's in a way hybrid social machine. And the result is audio set. So those are the fields that you can get, and then you see what is the description there. And then you might be like, well, this is not really that universal, because the way that something is described in English, or the way that something is described, already presupposes some interest or way of using the sound. Like if it's musical, then you might be like, okay, what is the key? What are the instruments, and so on. So all those taxonomies have a use in mind, which makes it really difficult to reuse sometimes the sound, the language, linguistic labels in other tasks of retrieval. So this is over 632 classes, or event classes. Those are the fragments that were labeled. And it covers like quite a bit of the space of sounds that we can recognize in the wild. This is important because all these machine listening systems or arbitrary systems that are either retrieving information from the environment for, say, ecology, like species and animals, birds, and so on for conservation, then those categories are going to probably be useful in order to sift through the things that you don't really care about, but also in general for other applications in health, assistive systems that you want to maybe detect a particular kind of event, like a fall or like baby crying and so on. Or gunshots or bombs and so on. So having a taxonomy of the different sounds is important, and this taxonomy is far from being complete. So this is why I add this fragment, which is not pessimism, it's more like what actually happens if we think that it's all about feeding like a neural network with more and more information, and then expecting the neural network to come up with universal taxonomy, which is kind of the dream of some researchers probably, to fully automate the future extraction. But then we see that the systems keep failing in different ways because there's specialist knowledge that is not captured by those taxonomies, even in the case of audio set. And I guess this is also relevant for you that are doing dynamical systems research or formal modeling of chaotic systems, because like we know that there's an issue with learning or machine learning in that there's a limit to the number of classes or the performance of a system across time. We have drift, like we have to keep updating the data set because it might be a mismatch between what the system is looking at in the real world and the samples that it was trained on, or just simply as a matter of adding more and more states to memorize, then eventually the saturation of states creates a system that will retrieve everything with anything. So it's funny that, I don't know if you have used, for instance, the Apple system or any image retrieval system. Sometimes you get kind of like identified pictures that are not really art with something that was, done like 10 years ago, and you're like, well, I just took a picture of my coffee or something, like clouds, and then it gets recognized as something else. So it's exactly this phenomenon that is reaching this saturation. So when you are super close to these attractors, which we could say that are the memorized states, then things will collapse, and as these things become super compact and super close to each other, then just very tiny variations that are not semantically meaningful will just send you to one retrieval avenue. And that can be useful if you use this for creating content, but it can also be an issue in content attribution when you are attributing some authorship or copyright to things that are not really easy to attribute. And we have another version of this by an Olympian. Olympo was experimental writing avant-garde club with mathematicians interested in creating literature based on constraints. So it's kind of like you constrain yourself to use only 3 vowels of the alphabet, and so on. So they play with this combinational aspect of creativity. He was well known for being, kind of like a compulsive collector and work as an archivist. And I think he was going to do some kind of research fellowship at the Uni of Queensland. Then suddenly died, and he couldn't come in there. But he left a series of writings about archives, and this one resonated with me because it's like, well, it's kind of similar to what Hopfield was saying, that at some point, the order that seemed to work, when it's expanded, and then when you keep adding more information, then it becomes, again, like an original anarchy, or even not more useful than the original state. Mm-hmm. Okay, so we could maybe say that there's no universal system, like maybe there's no Turing machine that can tell us what are the Turing machines that hold from all the possible Turing machines, but we can constrain the domain, and then we can do something useful, which is, as long as we don't ask things about everything, we will be fine, right? So not everything is lost. And this is why I guess maybe relaxing the constraints of search helps, and it is what I did, and this is the way that I defined foraging, which is more of a gradual emergence of constraints of the search. So it's not a super strict search. Then I'm not expecting any completeness. So I'm not expecting the system to tell me all the time if something is in the database or not. Like there could be some kind of graceful degradation or a compromise between the quality of the approximation to what I want and the actual performance of the system in real time. So search, to contrast search and foraging, search, I am defining this as search as something that needs a clear objective, and then you should be able to assert when the item is or not in the archive. Whereas foraging is more open-ended, more like, okay, we couldn't find this, but there's this and that is kind of similar, and then you might be interested in this, which is the case of content multimedia or recommendation systems use. So to this whole idea of search, there are plenty of methods or meta-heuristics that borrow inspiration from complex systems. Some of them that you have studied here, like the ant colony or swarms, that have interesting properties that can be used. There's even this field, the gradient-free optimization or evolutionary programming, which instead of using gradients is borrowing from behavior of complex systems. Particularly there, I situate my approach in models of fermions or electrons. The property that I use in this case is the diversity. So the model that I'm going to show you guarantees that the samples or when you're foraging, when you're exploring, the elements that you get are different between each other. And this is because of the model of the electrons has to take into account that they repel each other, they cannot occupy the same state, the quantum state. So from the Fermi statistics, we know that they cannot occupy the same quantum state, and they will repel each other. And this motivated Odell Mackey to formulate the DPP and represent, one of the cases is to represent the fermions in equilibrium. We'll talk more about what the second part means. So now, just bear with me. And the first part is all about how to use the behavior of electrons to make foraging possible. So those are the papers that inspired the DPP model. which is based on modeling the coincidence of electrons in space. So the case is that the repulsive behavior of the electrons is depicted there. And this is not like sampling at random. Like if we would sample independently at random, then we get more sampling like this. And then the clustering would be the opposite of the repulsive model, right? So those two analyses have a very general definition of, or yield a very general definition of the DPP. So what I'm going to just show you here is just the intuition. It's not like the most strict approach to them. There are not going to be any proofs here because I'm not working on the mathematics of the DPP. But that's quite interesting, something that I've been reading about. So the way that the DPP is defined is we can define a marginal probability on some finite subsets of Y. So think about Y as all my audio fragments, and then we have subsets of those audio fragments, which will be presented to the user as, hey, choose from these fragments, and those fragments will have the property of repulsion, so that means that they will be different between each other. So the requirements of this distribution, of this probability function, is that it has to be symmetric. In this case, represents a similarity metric of audio fragments. And if we restrict these different subsets to be of a particular kind or size, we call this a KDPP process. So therefore, we have this expression here, which is expresses the probability of the occurrence of those particular subsets, random subsets, as a function of the determinants of that similarity function. So I will give you an intuition of why the determinant is giving rise to the repulsive behavior. So think about having two elements only in that space, and then if we have two elements, then the determinant is just very easy to do, like high school determinant solution to simultaneous equations. And we get this here, and then we can re-express those two similarities, which are kind of auto-similarities. We can express them as two different DPP that are only one element, trivially. And then the other part is the ones that are not the same, right? So when the two elements on the side, when I and J, they will never occur when we have this case over there. So, and a large similarity between the values, like I and J, different values, will imply that this will be rare. So I think geometrically it's easier to see how this happens, but what will happen with the elements that are similar is that they will be collinear, and then the determinant will collapse, and the volume will be 0. And since the probability is defined in terms of the determinant, that means that the probability assigned to that particular subset from all the possible subsets will be 0, or will tend to 0 as I and J are similar, which is the case. That case over there. Mm-hmm. So that's geometric intuition. The different subsamples, the way that the matrices are formed are by we have this whole similarity matrix, a pairwise similarity matrix for all the fragments. We can compute it all, or use, factorize it or so on to optimize calculations. But we have this similarity matrix, and then we take sub-matrices of that huge matrix, and then those will define the probabilities for each subset. That's so this in this case, which is not defining a distribution formally, but just assigning probabilities to different subsets of this state based on the determinant. Mm-hmm. So that's what will happen. Say we have have a sample of 3 elements, and then determinant will be the volume. if the elements are too close, then the volume will be smaller, and then it will be less likely to be sampled. As an application, I thought, well, I want to use something that I don't really know much about, or that I haven't studied with other processes or classification systems. And then I found out that John Hutchinson's archive was publicly available through the State Library, and it was about 130 hours that I couldn't really go through manually. But I was very curious about what is in this huge library, because the way that the library is kind of offering access to this data set is not super accessible. We have like catalogs of species and so on, but then it's like very, very, very few people will actually listen to the whole thing. So one way of listening to those fragments and trying to find fragments that are more contrasting and probably characteristic was using DPP. So this is where the plunderphonics part comes in, which is like I use this system to create a real-time sampler of this data set. So I was given a sample every once in a while, and then I had to remix this live. So it was kind of like being a DJ, but then having these different fragments given to you, and then you kept layering them or discarding them, and then requesting more samples. And then you end up with a soundscape, which was the idea of this project. So the plunderphonics part comes from Oswald, experimental musician, and he used this concept to describe a practice of oral foraging, which made explicit that he was plundering content from the radio, from cassettes, and so on. So he was collecting those fragments like Leibniz, like the cabinet, and indexing those fragments himself. So he was doing something similar, and I made that connection. So it's just more of a conceptual relation, and then that's why I came up with that name, which is using the Fermions inspired process to create those compositions. But then there's also William Burroughs' famous approach to literature, which relies on recombining stuff, similar to the Mozart dice game, but with fragments. So that was very much Burroughs-like approach, but automating the indexing and adding this novelty property. And famously also, we know Ozymandias had also contact in this fictional world with William Burroughs and used those fragments to surveil the planet, in this case. And this also might maybe suggest other applications in ecology or in trying to find rare elements in longitudinal data and so on. So I think what makes this method interesting is that it's kind of simple. It's just based on a determinant, and it's easy to prove things about. Constraints, so it's kind of like Gaussian distributions. And it's also very easy to sample from, like to construct a way of sampling, because it's we are using a matrix, and then the matrix can be factorized because of the properties of that similarity matrix can be factorized, and then the complexities of algorithms that sample are around n to the power of 3. So it's not exponential. It's not like trying to go through all the possible combinations. And that's quite good for real-time performance. So the actual way that I define that, just to kind of maybe to ground the similarity function that I used, it wasn't a deep learning similarity function, so it's even cheaper to do because I don't need to train the system. So I used, this comes from that paper, use those two functions. One is based on wavelet scattering, which is like multi-scale approach to extract features at different scales of a signal and then compute the derivative. And then the other part is a scalegram, which is just a wavelet equivalent spectrum. And that gives me a feature, and then those values are used as the entries of that similarity matrix. The values are this is sort of the Hutchinson's archive, so the values are rendered on the right using UMAP, just to, more or less to give you an idea of what is the similarity structure, even if it's not not to be taken as a direct way of classifying those fragments, obviously. So from this was like, okay, I have this method, and I can use this to construct a way to explore a data set that then I can use to synthesize anything instead of using prompts. So the idea is that you use EPP to sample, say, receive a sample of 4 or 3 elements, and then you can listen to the elements. So in this case, fragments are 1 second. I will play two examples so you can see what is the contrast between them. So those are the 1 second fragments concatenated in the first case, and then similarly. So from those, a user selects 2, and then since I have the whole similarity matrix, the user can keep expanding that, like request samples that are around that particular fragment similar. So it's a good way of exploring, browsing through the foraging through the data set. And in the end, I will explain why I concatenate them. But the idea is that the user creates subcollections of those fragments and then creates sequences that concatenate them in so 1 second there. So can concatenate those different points by linking what is in between, like with a, in this case was with just nearest neighbors. So I kept concatenating elements that were in between. And in this way, the user can sort of create trajectories that they will be used to condition a system in order to generate them soundscapes. So those systems are not based on prompts. It's not like, please generate soundscape that has kookaburras and magpies and so on. It was more like based on those, in that subcollection created with the fragments, train latent diffusion, but on the latents, not on the raw audio. So first I trained variational autoencoder, which is a model that is used for generative audio, in general to a generative model for anything. So in this variational autoencoder, you give the autoencoder a vector, and then you can retrieve or regenerate, resynthesize things from that archive. So I trained this at the Dolby clouds, and then after 7 days, I could reproduce a fair image of this archive. And then on the side, I use a latent diffusion to generate the latents that then I would use to retrieve or to sample from the autoencoder. So this latent diffusion part is where the collections of the user go, because then the latent diffusion will generate samples that reflect the decisions that the user took. And then those vectors, the concatenation vectors, the latent diffusion will create latents that then will be fed to the variational autoencoder, or will be used to retrieve audio. So I did this with my own collection, and then the two results were this. I'm going to play the 2 examples, one after 7 days of training and one after 16 days. This is all the synthetic. Mm-hmm.
So the input for this is the two short segments you had on the previous.
Yeah, I have a diagram to explain it. Yeah, good question. So this is the synthesis pipeline. So I have an archive, and then we generate the trajectories with the DPP. Then the user has those trajectories. That's one phase. Then I train the RAVE. The RAVE has an encoder and a decoder. So this is trained using one of the different objective functions. Could be the Wasserstein or the classic function. And then after the training is done, the purple part, which is that loop is pretty much the propagation of the error, the reconstruction error, and the constraints of the optimization part. Then after that, then those user trajectories are encoded by that pre-trained encoder. Those are frozen. No, they are not touched at all after being trained. Then I have those latents, which are like indices or like keys of the cabinet. And then those latents can be used to train that diffusion model. So I'm training the diffusion model on the keys, not on the output. And then I get the diffusion model generates keys of arbitrary size that reflect those latents. Then I feed those keys that the diffusion model creates. The diffusion model is actually quite fast to train because I'm training it on not on audio, which is high resolution, so 512 or multiples of that, vectors of that, multiples of that size. And then those vectors are fed to the decoder. Then the decoder generates those examples that I showed you.
In that diagram, is it the choice of latents that dictates whether you get a viral or magpie?
Yep. I mean, that could be something that was not in the trajectories. So you could use a huge RAVE encoder train on a supercluster and then just let the user do the other part. So that is kind of like enabling more customization at a lower cost and reusing those fragments. It's kind of like the idea of the cabinet. You could reuse a cabinet of Leibniz to write something else that is not Leibniz and automating that search process. Yes, the latents are of the paths of those full concatenated audios. I think I didn't show you the concatenations. Yeah, this one. Mm-hmm.
So you choose something from A, choose something from B, get a
Yeah, that was the naive approach of just using like something in between. Could be just something more conditioned on how the sequences could be concatenated, like more of like consistency, so there are no jumps and so on. But I guess that didn't matter much because I wasn't going to use those directly. They were just going to be the keys, the material for the keys. So that's what I did in the end. And then I noticed that obviously you get these verbatim reproductions of the archive that if you don't know the contents of the archive, it seems that, oh, it's new that the machine came up with something different that hasn't been there. But this proves that you can keep recombining things and then eventually you'll get something that was there. That kept happening, and then you could explore different combinations. It's kind of like interpolating different latents and then get something hybrid in between by using those trajectories. But in the end, there was nothing really new that wasn't in the archive, right? So this is why I add this. It's kind of more of a critical quote by Jean Paul, and then it's that that he couldn't tell when a book was created by recombining these fragments when it wasn't. Which happened sometimes with this archive. It was like, oh, that sounds almost like a recording.
So back to your the hot field quote from earlier and your soundscapes. So you get like a finite fragment out. If you keep running that forward in time,
Oh, that's a good question. I mean, you can say that the user can, keep the user is kind of like a recursive function of that keeps selecting over and over and over until the cabinet is so customized that it can produce or is in a stable state that reflects the taste of the user. So we could say that there might be some convergence, and that's what we actually want, maybe in the case of a generative system for customization. And the DPP facilitates reaching that state. Like it's kind of like optimizing the, like numeric methods for solving a system by actually finding the points that have more information. Yep. So to summarize, DPP offers an avenue to explore those generative systems and very large spaces of collections in a tractable way. And this is because of the novelty or the repulsive property. So these three areas are going to benefit from this approach, which is first the exploration of large corpora without necessarily listening to it. It also works sort of like a compression approach by sampling novelty. But we could also use it in synthesis as a show with the creation of trajectories, and to control ultimately systems that we don't have labels for. So we cannot describe some of those birds because we don't even know the species, and we might have a reference that we could use as a key and then retrieve something and then use that in the process of trajectory concatenation. And so my findings were that more like qualitative findings in this case, because more like the numeric quantitative part is what went into the model, Dolby. So we can tailor the performance of the generative models. They actually require extensive fine-tuning. That's time-consuming and sometimes doesn't yield the best results. But we can perhaps optimize that or make it a bit more efficient with DPP. This also works when we don't have ontologies for the things we want to generate. And sometimes those ontologies might actually create collapsing states that are not interesting. So we end up kind of, everybody ends up producing the same. Everybody has the same cabinet because of the way that the ontology is kind of, constraining the exploration process. But also we can use that in order to improve the ontologies by, say, sampling and then using DPP to sample sets so the humans can label them. And then you actually label novel points, so it's not redundant labeling. So that can be used more on the side of kind of mechanical Turk or Dallinger, like there's this other platform for experiments, which relies on that distributed human-machine interaction. The trajectories are one example of that. So I guess the rest of the session